Okay, I'm just kind of guessing where we got to in class, so let's kind of see what happened. Stop, Nolan. I need you to go play. I'm not joking. Okay, so it says, based on what we've seen, does continuity imply differentiability, or does differentiability implies continuity? So remember that even if your function's continuous, like we saw, it could still have a cusp. So it's not going to be that way. So in order for a function to be differentiable at an x value, it must be continuous. Okay? So we can say that differentiability implies continuity. What this means is if a problem tells you that a function is differentiable, that you also mean it's continuous. Okay? That's what it means. It implies continuity, because it can only be differentiable if it's continuous, and as we saw, just because it's continuous doesn't mean it's differentiable. So it says, in order for a function to be differentiable at a value in x, two things must be true. One, oh, that's not what I wanted. F of x must be continuous at x equals a. And the other part that must be true is that the limit as x approaches a from the left of the derivative must equal the limit as x approaches a from the right of the derivative. So basically the left and right hand limits need to be the same. What I like to think about is that there are 4 places where your graph is not differentiable. One of those is at a discontinuity. One of those is at, think about a jump or an asymptote. Those would all be discontinuities. But what else? At a cusp, at a corner. Those are places where your graph is still continuous, but like this, right? Like we've seen, those are a cusp and a corner, which are kind of the same almost. And then the last one is a vertical tangent line. And remember, we talked about that because a vertical tangent line is kind of like the cube root of x. There's a good example of that where it goes like this. Oh, that's terrible. Should turn like this. But if your tangent line is undefined, the slope is undefined, then there's not differentiable there. Okay? So it says consider the function g of x equals da da da, another piecewise function, right? So it says, is it continuous? We did this way back in the very first unit. If it's continuous, we just want to check that it meets up at 3, right? So basically, we're checking that the limit as x approaches 3 from the left of g of x equals the limit as x approaches 3 from the right of g of x. Oh, and please get out of my stuff. And so from the left, that would be here. So I'm just going to plug 3 in there and set that equal to plugging in 3 to the right, and that would be 5 minus 3. So the square root of 4 is 2 equals 2. Yes, it is continuous, right? Yes, because the limit as x approaches 3 from the left of g of x equals the limit as x approaches 3 from the right of g of x. And if you remember that whole definition of continuity, the limit exists, and g of 3 equals the limit as x approaches 3 of g of x. That's kind of our 3-part definition. So it's defined, it equals 2, the limit exists, and the limit equals that. That's kind of our 3-part definition. But the new part is it differentiable at 3? So step 1, if it's continuous, it's differentiable. So we can say x equals 3 is continuous, so that's one thing to check. Without graphing it, it's hard to know, is there a jump or a hole in the graph? We know there's not a hole because it's continuous. That's where we can look at the derivative. So like, is the limit as x approaches 3 from the left of g prime of x equal to the limit as x approaches 3 from the right of g prime of x, which means we need to take the derivative of both sides. stop, man. You take the derivative of each side. So this one, the top one would be, so that's x plus 1 to the 1/2. So the derivative of that would be 1/2 times x plus 1 to the negative 1/2. And the derivative of the inside is just 1. And the right side derivative is just negative 1, right? So this would be 1 over 2 times the square root of x plus 1. And we got to plug 3 in there, right? So the square root of 3 plus 1 is the square root of 2. Well, I can say right now that those are not equal to each other. So g of x is not differentiable at x equals 3. And I didn't even have to graph this. I can tell that there must be a corner or a cusp because the derivatives don't match. But we can just say because the limit as x approaches 3 from the left of g prime of x does not equal the limit as x approaches 3 from the right of g prime of x. We're checking, are the derivatives the same from the left and the right? Because we can't graph all these. So this is more like a question that I've seen on, oh my gosh, on the AP exam. It says, for what values of Kmn will the function be both continuous and differentiable? And so we've done this before for continuity, but now we're adding in that it's differentiable. So again, what are we checking? If we want to check that it's continuous at x equals 3, we're going to just check that the limit as x approaches 3 from the left of h of x equals the limit as x approaches 3 from the right of h of x. So from the left, if I just plug 3 in there, that would be k times the square root of 3 plus 1. And over here, that would be 3m plus 2, right? And the big difference here is that we don't have enough information to know what k and m are. I can say 3 plus 1 is 4, so that would be 2k equals 3m plus 2. What else can I do? I can take the derivative of this, right? So if I want to prove that it's differentiable at x equals 3, I can take the derivative. So basically, I'm going to do the limit as x approaches 3 from the left of h prime of x and set that equal to the limit as x approaches 3 from the right of h prime of x. And take those derivatives. And so remember that k and m are constants, so kind of just ignore that out there. So that would be the k times x plus 1 to the 1/2. So the derivative of that would be k times 1/2 times x plus 1 to the negative 1/2. And again, even though it's chain rule, the derivative of the inside is just 1. And over here, the derivative of mx, like if it was 3x, the derivative is just 3. So the derivative of mx is just m. And then I still have to plug 3 in here, but I'm going to kind of simplify it as I go. So on the top here, I have k over 2 times the square root of, I'm going to plug 3 in here now, equals m. So that would be 3 plus 1 is 4, square root of 4 is 2. So k over 4 equals m, or could I say k equals 4m? Do you agree with that? So could I do some substitution here maybe? If k equals 4m, could I plug 4m in here for k? And then I would get 8m equals 3m plus 2. So subtract 3m over, and I would get 5m equals 2, or m equals 2/5. And then plug back in over here, k equals 4 times 2/5, or k equals 8/5. So hopefully that's some kind of memories for you, that we've done that kind of stuff before. Let's look at this last one here. It says, for what values of a and b will the function be differentiable? Same idea, they're just higher values. Notice that this one just says when will it be differentiable, but remember that it also has to be continuous to be differentiable. So you still are going to do it the same way, right? Right there. So if it's continuous, right, I'm going to check the limit as x approaches 1 under the tape from the left of f of x and the limit as x approaches 1 from the right of f of x. I'm just plugging 1 in there. So that would be 3a plus 2b plus 1. And this would just be a minus 4b minus 3. Right? This looks a little more complicated. I don't know what we want to do. We could subtract this a over and get 2a. We could add this 4b over and get plus 6b. Subtract this 1 over and get negative 4. Right? And then at some point maybe we could divide by 2, or let's just leave that for now. I'm going to erase this. The other side of this, I need to do the derivatives, right? I need to do the limit as x approaches 1 from the left of f prime of x and set it equal to the limit as x approaches 1 from the right of f prime of x. And by writing this statement up here, you don't have to say, I'm checking to see if it's continuous and that the derivatives equal each other, right? Like it saves time, I think. A and b are constants, right? So the derivative of the left side would be 6ax plus 2b. And here would be 4ax cubed minus 8bx, right? Oh, minus 3. I'm out of room. Nolan, please stop, buddy. It's not funny. And then at x equals 1, right? So that's where you get rid of the x's. It's just 6a plus 2b equals 4a minus 8b minus 3. So we can put those together. So I can subtract the 4a over. That would be 2a. I can add the 8b over, and I think that would be 10b equals negative 3. And now, instead of solving for 1, I think this works out really well to be elimination. So I'm going to leave you to do this and see if you can get the answer. I would just subtract negative here. I would make this negative 2a minus 10b equals positive 3. Like change all the signs of this, because then these just eliminate and you get negative 4b equals negative 1. So b equals 1/4. Then you have to plug that back in somewhere. I'll just plug it in right here and get 2a plus 6 times 1/4 equals negative 4. Nolan, you're going to get in trouble. I don't know. You have a calculator here. You could do what you want here. I just reduced 6 over 4 to 3/2. I'm going to multiply everything by 2 just to save my fractions for the end. So I'm going to say 4a plus 3 equals negative 8. So then I subtract 3 and get negative 11.